a bouncing ball. We're going to model this in Python. We're going to jump right into it. We're going to go as much detail as possible. We're going to start off with a simple model and then go to a more complicated model. So here's a ball and there's a ground. And I know I have a gravitational force acting on that. And I can let the ball fall and I can model this in Python, and we're going to do that. So I'm going to go ahead and talk about the physics of two things right here, and then we'll model it. So number one is, if I have a falling ball, that's pretty easy. But we can make it more complicated, which will be useful for later. If I break this into small time steps, delta t equals 0.01 or even smaller seconds. And during that time interval, I can calculate the force. F net, in this case, is just mg. And that's the change in momentum with respect to time. And if I have a short time interval, I can assume this is constant, because it is in this case, which means that I can write this as P2 minus P1 over delta t. That's the momentum at the end of the time interval, the momentum at the beginning. I'm flying through this part because I suspect that if you're looking at this, you've seen this before already. If I solve this for P2, I get P2 equals P1 plus F net delta t. So if I know the momentum at the beginning of the time interval, I can find it at the end if I know the force. And then I can do the same thing for position. So here's my position R, in general R. I can assume that the momentum's constant, so that the V average is P2 over m. I'm using the momentum I just calculated, and that's going to be delta R over delta t, and that's going to be R2 minus R1 over delta t. And then I can solve that for R2. R2 equals R1 plus P2 over m delta t. And so this is my Euler method of a numerical calculation. Calculate the force, update the momentum, update the position, go back up and do it again. And if the ball's just falling, it's stupid and easy, but we're going to do it anyway. Okay, now, but what happens when it hits the floor? Right? How do I model a bounce? And this is just a simple point particle model of a ball. We're going to obviously make a much better ball later. Well, number one, I'm going to do this two ways. One, actually, I'm going to do it one way. The easy way is just when if hit, let's say if hit, reverse momentum. I can't spell it. Reverse P. And technically, that's not going to do it, because if I had a ball coming in this way and reverse the momentum when it hit, it'd go back that way. So instead, I want to reverse Py. So I want to multiply Py by -1. Now, that works and it looks fine, and you may want to do that if you're doing a video game, but let's not do that. Let's do this method, 2, if hit, spring. So let's say that the floor is a spring, and if I calculate this distance between them, I can say there's an upward force from the floor, F floor, equal to K times S times Y hat. So that's a unit vector, and K is a spring constant. Let's call that K1 for the spring constant on the floor. And if it's not hit, if they're not overlapping, there's no force. So that will change this up here. That's a lot, but let's just go ahead and do this from scratch, build this model. And then I'm going to make a much better model. And if this takes 5 hours to do this, I'm going to make a 5-hour video. It's not going to take 5 hours. But I'm using Web VPython. Web VPython is my weapon of choice because, one, it's on the web, and I like that. I don't have to install anything. 2, it has these very, very nice visual objects that we can build. And 3, it's got vector support built in, so that's just nice. Let's just jump right into it. Make it bigger. G equals vector 0, negative 9.80. I need the gravitational field G. Now, let's go ahead and pick some values. R, the radius of my ball. I'm in my head, I'm a 5 centimeter radius, which is kind of big. No, 0.0, that's not big enough. 0.02, 2 centimeter ball. So it's a good size ball. And then H is how high I am above the floor. So let's pick 1 meter. I need the mass too, but I'll put that in later. So let's start off with the floor. If I have a 1 meter height, if I put the floor at 0, then it's gonna Web VPython's gonna kind of shift it so that that's in the middle. I want it shifted down. So let's just put that at negative h/2. I'm gonna make the floor. Floor equals a box, which is a built-in object in Web VPython. I need to give it a position, vector 0, negative h/2, 0. I need to give it a vector size, the length, the width, and the height. It's also a vector. Let's say 2 meters, 1 meter. The height is going to be 0.01. Yeah. And then the width, let's say 0.2. Let's just run that. I like to run things every time I build something. So there's my floor. That looks nice. That's a nice floor. And I guess I could save this too. Bounce 1. Simple. We'll make a new one for the new one. Okay. Simple bounce. Now I need to make my ball. Ball equals sphere. Position is going to be equal to box.pos. Right? The position of the, floor.pos plus vector 0h0. So that means it's going to be h above that. And now technically that's from the center of the box to the center of the ball, but it's fine. I don't really need that anything. I need the radius. I'm going to say it's r. And color, color.yellow. That's good enough. Now I'm going to give it a mass, ball.m. It doesn't really matter, but I'm going to pick this. 50 grams, 0.05. I need an initial momentum to change momentum. Ball.p equals ball.m times vector 0, 0, 0. And this is a great point where it's like, hey, the 0 vector is a vector, right? And that's something I think is important in the lecture physics class, even when you're not doing numerical calculations, to realize that the 0 vector is not 0. Okay. I need the spring constant with the floor. K1 equals, let's say it's 100. I'm just picking a value. We can change that. Now I'm also going to pick something called S0. S0 is the distance between the ball and the center of the ball and the center of the floor when they're not compressed. So if the distance between them is less than this, that'll be important. And I can use it's kind of calculate. It's the radius of the ball plus half the height of the floor. So r, which I can just use r plus floor dot size dot y over 2. And that's a lot in there, but it's fine. Okay, I think that's good. Let's go ahead and put a time step dt of 0.01. I think that should be good enough. Yeah, let's go to it. While t is less than 1, I'm going to do it for 1 second. Rate 100. So this says that since I have a time step of 1/100th of a second, a rate of 100 says don't do more than 100 loops per second, and it will run in real time. So the first thing I'm going to do is to calculate. I'm going to ignore the floor first. Let's just get it to run without the floor. So I'm going to calculate the force, Fnet. I'm going to call it Fn. Will be ball.m times g. And notice that g is m times g, where g is a vector. I'm not doing negative mg because I'm dealing with the vectors. And that's going to make f a vector. This is what's awesome. Now I can update the momentum of the ball, ball.p plus fnet times dt. Now I can update the position of the ball. And in this case, I'm not using r. I'm using ball.pos because it's an actual object. It has an actual position. So ball.pos plus ball.p times dt divided by ball.m. Now I need to update time, or the loop will run forever. I've done that many times. If you do it, stuff happens. T equals T plus dt. Let's run it and see if anything works. Let's put a make trail over here. Make trail equals true. This would just mean the ball will leave a trail behind it. That's kind of cool. That's a long time to fall for a second. That's fine. That's about right. So it went right through the floor because we never told it to do anything with the floor. So we need to do this. Down here, I'm going to make a new variable called floor equals vector 0, 0, 0. And this is in the loop. This is the force that the floor exerts on the ball. Every time I get back to the top of the loop, I'm going to say it's 0. That way I can just change it if I have to, but it's default 0. And that means Fn plus F, oops, not that, plus FF. So I'm adding those two together. And if it never collides with the floor, nothing changes. Now let's calculate, I'm going to calculate S. S is the distance between the center of the ball and the center of the floor. So ball.pos minus floor.pos. And you could set the floor as 0 or something like that. It'd be a lot easier. But this is better. And that's going to be a vector pointing down. That's fine. If the magnitude of S is less than S0, then there should be a collision. And in that case, I need to calculate the force. FF is going to be equal to K1 times the magnitude of S times y hat, vector 0, 1, 0. Now you might think, hey, why not just use S hat for the unit vector? Oh wait, S minus S0. That's lowercase s. And I always get the direction backwards here. So let's see. K, if it's below it, so that's going to be smaller. I'm going to subtract that. It's going to be a positive number. That's going to be a negative number. So I need a negative sign right here. But the problem is you can't use S hat for the vector to make this a vector, because imagine that the ball is not right in line with the floor, and so the S vector, oh, this is actually wrong, because it assumes that I'm dropping it right over the thing. So I actually need to do this. I need to do S dot Y minus SO. Yeah. Because I only care about the Y component. That ball.py, yeah, that'll work. Because the floor and the ball X position might be different. So when I take that S vector, it could be some weird thing. It could be. And I think I messed up in my previous version of this, but that's fine. We'll fix it. Okay, let's see if this works. And this is why it's good to start off with simple stuff, right? See, that didn't work. Okay, so a couple things. Did I get that sign right? That's my first option, that I got that sign wrong. Let's just try that. Hello? Oh, that did not get it right. Why? Maybe it's not. Let's see. S dot Y minus S0 is a number. S dot Y. Ball.pos minus floor.pos. If the mag of, let's just say S dot Y. And let's print bounce. I don't even know if my condition statement's working correctly. Okay, so it is bouncing. It's calculating that. It's setting F to this value. Maybe I just need to increase that. And then it is doing this too, so it should work. Okay, that worked. And that shows that my negative sign was indeed negative. So this is negative. There we go. Bouncing. So if I just had my spring constant was too small, It seems like it would indeed stop eventually, but it just kept going. That's fine. Okay, so we got our simple bounce model. But you notice it bounces the same height it was at. There's no rotation or anything like that. So let's make a better and more complicated bounce model. So let me go over here. I'm going to copy this stuff, all this stuff, just so I don't have to redo it. And let's make a new code. And what I want to do is replace my ball with 2 balls connected by a spring. I save that. New trinket. Web VPython. You can't see that. And then I have to say this. And paste all that stuff in there and run it just so I can save it. That's fine. And this will be 2 mass spring ball bounce. Okay, let me switch over to the paper and show you the plan here. Going back to the paper. I need to give my ball some internal structure. I'm actually going to build the ball like this. I still have the floor. And here's my new ball. So it's going to be 2 balls inside of the ball connected by a spring. And then if either of these balls hits the floor is going to push up. But these balls can oscillate or rotate and do all sorts of things. So I need a couple things. I'm gonna put my masses right here. I'm gonna call this one A1, and I'll call this A2. And then I need a unstretched length L0, and then I can calculate the length between these and make my spring. I have to start off with some unstretched length because I don't want them oscillating beforehand. And then I can calculate the center mass and put the center mass in there. Remember, if I want the center of mass will be the ball, I'll call that R center of mass. It's going to be equal to A1. It's called R1 is the position of that one. R1 M1 plus R2 M2 over M1 plus M2. And so, but I'm going to have another spring. This will be K2, and this is K1, the spring constant. So I have a bunch of things I got to do. Let's do that. It's going to be awesome, maybe. But I'm probably going to mess up, because that's what I do. Okay, so I still have the same G. I still have the same R. Let's make R bigger, just so I can make my box look a little bit better. I mean, the thing inside. So let's make it a centimeter. Let's see. Is that going to look good? No, I did 20 centimeters, 2. That's fine. I still got my floor. I still got my ball. And the ball is going to be my big thing. And so let's make it, I'm not going to make it yellow. But I am going to make, and I'm not going to give it a trail. But I am going to make it see-through. Opacity equals 0.4. The ball will be the total mass, momentum, all that stuff. I think this will be fine. Let's just run this and see what it looks like. It didn't. Oh, there it is. There's my see-through ball. Okay. Now I'm going to make 2 interior balls. I'm going to call them A1 and A2. I don't actually want to have anything. A1 is going to be, let's call this, what did I call it before? RCOM. Let's make a center of the ball. RCOM equals sphere. Position equals ball.pos. The radius is going to be equal to R divided by 10 maybe, and make it a color red. Color equals color.red. Let's see what that looks like. Yeah, that looks good. Now I'm going to make my 2 balls. I'm going to call them A1. A1 is a sphere. Its position is going to be, I'm going to have it straight up. So it's going to be rcom.pos, right? The center of mass plus the radius. rcom.pos plus r times vector 0, 1, 0. And then the radius of this will be, what did I use before? 0.05 radius. 0.05. Color is color.yellow. And then I'll make another one, A2. A2 is a sphere. Same thing, except copy. And it will be -1. Okay, let's run this. So there's my two balls. Now, that looks a little weird. I actually want to make them a little bit less than the centers of them are at the edge. Let's just put this at 0.8 times. 0.8 times. And let's run that. That looks better. Okay, now we can also put a spring connecting them. We don't have to, but we're going to. A spring connecting them. Oh, I do need to give them both a mass. A1.m equals ball.m divided by 2. A2.m equals ball.m divided by 2. Because they're the ball, right? They're the actual, these two masses are the ball. Spring equals a helix, and the position is going to be equal to A1.pos. Then I have an axis, which is the vector from A1 to A2. So it's going to be A2.pos minus A1.pos. And then I need a radius. And the radius will be the radius of the coil. Let's put this at 0.02. Let's just try that. And the thickness is going to be changed too. But yeah, there it is. Let's make it. Let's leave it. That's fine. Okay. I need one more thing, K2. Let's put this at 200. So there I have my thing. Oh, I do need L0. I'll put it right down here. Am I in the screen? Yes. L0. L0 is going to be equal to the magnitude of A1.pos minus A2.pos. It's how far apart they are, the distance. Okay, let's get on with it. T is 0, dt is 0.01, while t is less than, let's do 2, rate 100. Now, I have two net forces. I only have two objects that have forces on them, and that's 1 and 2. I want to model this without interaction with the floor first, and then we can add the floor. Okay, so F1 equals A1.m times g. That's the mass. That's the gravitational force. And then I need the spring force. And there is a spring force. So let's do this. L2 to 1. L21. I wrote this down somewhere. L21 is going to be the vector from 1 to 2. I'm going to get this right. I always get this backwards. Let's do L2. Yeah, it's going to be the vector from 1 to 2. So it's A1.pos minus A2.pos. I'm trying to set it up so if we do 3 masses, we can do the same thing. Now I can calculate the force. I need the magnitude, the difference between the magnitude of that and the L0. So I'm actually going to call this F21 is the force on 1 due to 2. It's just a good idea. Oh, let's just call that, actually, let's call that F21. It's just a spring force. Negative K2 times L0 minus mag L21 times norm L21. So in this case, I do need to use that unit vector connecting the two things, because if they rotate around, I need to know the direction of that force. Now, there's only one spring force, because there's only one spring. And I calculated the spring force on 1 due to 2. But now I can use that. I don't have to redo it for the other mass. I can calculate F1 is going to be equal to A1.m times g plus F21. F2, this is the force on mass 2, is A2.m times G minus F21, because that's the equal and opposite force. So it should work. Now I can use the forces to update the momentum, update the position, update time. A1.p equals A1.p plus F1 times dt. A2.p equals A2.p plus F2 times dt. Update the positions, A1.pos, A1.pos plus A1.p times dt divided by A1.m. A2.pos equals A2.pos plus A2.p times dt divided by A2.m. And then update time, t equals t plus dt. Remember, no interaction with the floor. There's no interaction with the floor. It should pass right through the floor. It really shouldn't do anything because the two balls are not compressed or stretched, so they should just fall. Should. Sometimes you make a mistake, so you got to really check the stuff. Save it. Run it. See? Mistakes were made. Undefined A1.p, because I left off a thing. A1.p. Where? Oh, I never set those. I never set the initial momentums. A1.p equals A1.m times vector 0, 0, 0. A2.p, and I just see something else I messed up, equals A2.m times vector 0, 0, 0. But I'm going to run it just so we can see. Maybe you already saw what the problem is. There is a problem. Not a big problem. There's my problem. Oh, it exploded. The problem, it looked like it was falling fine until it just kind of got out of control. But the problem was that I didn't move the ball, I didn't move the center mass, I didn't move the spring. So I do need to move all those things. Maybe I shouldn't do this for 2 seconds. Let's just do this for 0.5. So I need to move all that stuff. So let's recalculate the center mass. I'll just do it in one thing. rcom.pos equals A1.m times A1.pos plus A2.m times A2.pos divided by A1.m plus A2.m. That's the recalculate the center mass and move the thing. Ball.pos equals rcom.pos. Now I need to move the spring. Spring.pos equals A1.pos. That's what we had before. And then I need to redo the axis because A1 and A2 moved. Spring.axis equals A2.pos minus A1.pos. Let's see what happens now. Okay, it blew up. That was really weird. Why did it blow up? That shouldn't happen. Something happened when it hit the floor. F, L1, K2, L2, norm, K2 is 200, F1, F2, A1, A2. Huh. Why did it blow up? I mean, it literally blew up. Watch. I'll run it in slow motion. Falling, everything looks good. And then they just... I wonder if I got this negative sign wrong. Right there. And they're pushing each other apart. That's what I did. And so you get a small rounding error makes them move apart, which means that they're pushing each other apart more and more and more and more. So that's what the problem was. My fault. Okay. Fixed it. Now we need to include an interaction with the force. So I'm going to, the floor. I'm going to go ahead and put here F1. Did my camera turn off? No, it turned upside down though. Okay, that's fine. F1 and down. Oops, that's not what I want. Hello. And right here plus having a lot of problems here, plus FF2. Now that's the floor pushing on 1 and the floor pushing on 2. So I need to set those equal to 0. FF1 equals vector 0, 0, 0. FF2 equals vector 0, 0, 0, 0. And now I'm going to calculate those S vectors. So I'm going to say S1 is A1.pos.y minus floor.pos.y. And yeah, that's a scalar. S2 is A2.pos.y minus floor.pos.y. So again, I don't want to look at the x components for these vectors because the floor has a center, right? And if I'm over here on the side, it's going to look at that, and I don't want that. I only want the y components. Now I want to see if there is a force. If S1 is less than S0, then I need to calculate the force. And it's going to be the same force I had before, which I don't really remember. F1 equals K1 times S1 minus S0 times vector 0, 1, 0. So let's see. If they're shorter, if it's shorter, then this will be a negative number, right? So I actually need a negative right there. And then I need to do the same thing for mass 2. If S2 is less than S0, colon, FF2 equals negative K1 times S2 minus S0, S0 is a big mistake, times vector 0, 1, 0. Let's see if there's about, I want to change this to 2. This could blow up. Could blow up in my face. That happens. Oh. Look, it's bouncing before it even gets there. I feel like this is the problem. A1.pos.y minus floor.pos. Oh, floor. No, that's right. Floor.pos.y. It falls fine. Is my spring constant too high? Let's change this to 500. See if maybe it just looks like it's not hitting. See, it's like the floor is at the wrong, that looks good. But the floor is at the wrong spot. Oh, that's why. Because I'm using S0 for the radius of the whole sphere. So this should be A1 dot radius. Okay, and so you can see the internal shaking of the thing. That's exactly what I want. I want it to be shaking a little bit less. So let's call K2 100. I want a better oscillation. That's pretty good. That's pretty good. Let's go ahead and just see. Let's make a graph of the height of the position as a function of time and see if it's not bouncing as high. And I'm going to make this actually a little bit less. Let's make this 80. I don't know where I came up with that number. So up here I need a graph. G1 equals graph. X title equals T. Y title equals Y. Lowercase y. Width, that's right. Let's put 400 by 200. Height, 200. And I'll call it Fy equals G curve. Color equals color.blue. Down here, I need to add in that plot. I'm going to do it before the time. F1 Fy dot plot T. And then I'm going to plot the center of mass. Rcom dot pos dot y. And it actually went lower. Look at this. It started right here, and it went lower, then it went higher. And it actually went lower, then it went higher. And it 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 went lower, then it went It shouldn't go higher. Let's see if this does it. Let's do 0, 0. When in doubt, make the time interval shorter. It's a little bit less. Okay, let's change that spring constant so that it oscillates even more. 50, 30. Okay, so it is bouncing less and less and less. So that's pretty good. There's a whole bunch of stuff to play with. I want to do one more thing because this video is getting too long. I do want to make a 3-mass ball. And we'll use the same ideas. So that won't be, well, I'll build on this. But now, what if I have it like rotated? So then when it hits, when one ball hits, it can cause the whole thing to rotate. Let's just rotate this initial ball. Up here, when I make these, let's put theta, let's give it a 20-degree rotation. Theta equals 20 times pi over 180. Now, that ball, I need to shift it, right? I need to shift ball A. I'm going to shift it to the left. So that's going to be, if the angle from the vertical is 20 degrees, its x component is going to be sine. So I'm going to say sine, negative sine, theta. Not that. And this will be cosine theta. Right, so then that's my y component. It's cosine theta. My other one's negative. And then for this one, it's going to be negative cosine theta. And then sine theta. Let's see if that runs. Okay, that's pretty cool. I like that. I mean, it did something weird, right? It kind of sat on the ground, but energy's still conserved. The energy of this ball should still be conserved. And you'll notice that it can actually make it bounce up higher because once it's oscillating and spinning, weird things can happen. I can make it mostly just spin by increasing the spring constant to something much higher, 120. Let's do that. It still spins a lot, but there you go. It's a more real, it's not a perfectly realistic ball, but it's more realistic. It shows what happens to that energy of the ball when it collides. There's some internal structure going on that makes things happen. Total energy should still be conserved. And that's something that you can do. Check. Is the energy, is that the kinetic energy of the two balls plus the spring potential energy plus gravitational potential energy, is that constant? It'd be fun to check. It'd be a good homework problem. Okay, so that was a lot. I want to make a better one. I'm going to do that, but again, 38-minute videos I don't normally do. So, and if you went through this whole thing and made it to the end, then you get a double thumbs up. 1 thumbs up, 2 thumbs up. That's pretty good. So, and I think there still may be some errors in my code, but you're getting the idea. I will show you a 3-mass one in another video, I promise. Links to the code down below. Those two, the simple ball and this one. Later. You're still here. Okay, I'm going to go. I'm really going to click go now. This is it.